Okay, everybody can hear me okay? All right, we're going to switch gears just a little bit since we're leading into Thanksgiving, and I'm not going to give you homework over Thanksgiving. So I'm going to introduce some stuff today, and then we're going to work on it for a little bit in class, and then we'll look at a solution, then we'll work on it a little bit more and see how kind of that goes. So kind of do an in-class exercise today. And it's something you may have heard of before. It's something called Conway's Game of Life. And we're going to try to do this in the context of our threads that we've looked at recently. So we're hoping to get a program that ends up, ours is probably going to be text-based, but a program that ends up looking something like this in the upper right-hand corner here, where we have some interesting patterns emerging, and this is based on something called Conway's Game of Life, where this guy is represented as like a two-element or a two-dimensional grid. So we have rows and we have we have rows and we have columns. All right, and there's some rules. So the rules say that any living cell, so that could be a cell with like a 1 in it or a cell that's on. So we're calling each little bucket in our grid, we're calling that a cell. All right. And we're saying that any live cell with fewer than 2 live neighbors dies as if by underpopulation. All right. Any live cell with 2 or 3 live neighbors lives on to the next generation. So we're going to think of a generation as being something that maybe happens every second. You know, we'll have a thread that'll sleep for a second, then update itself. So we almost get like think of it like a flip book cartoon type thing. And then any live cell with more than 3 live neighbors dies as if by overpopulation. And any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. All right. So the idea is, let me get Keynote open here. All right, we're going to be looking at databases next week. Okay. I think this is kind of where we are here. Let me hide this. All right, so this is just one little section of, let's say, a larger grid. All right, so each of these guys is a cell on the grid. And what I'll actually do is I'll make all these guys red for right now. Red indicating that they're currently dead cells. All right. And let's just say that we are trying to make a determination about what happens to this cell right here next. All right. So the Game of Life rule says that any dead cell, well, any live cell with fewer than 2 live neighbors dies. So for instance, if this guy was alive and this guy was alive and this guy is currently also alive, if we're looking at, let's see, we need fewer than that. So it says fewer than 2 neighbors, right? Any any live cell with fewer than 2 live neighbors dies. All right, so from this guy's perspective, when we're looking at this particular cell right here, we're saying that how many live neighbors does he have? Is this guy alive? No. Is this guy alive? Yes, that's 1. No, 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 no. So his neighbors are all the cells that, touch him in some way. All right, so in this case, this guy has 1 living neighbor. So then by the rules of, so if he's currently a live cell, which I've advertised he is, and he has less than 2 living neighbors, he only has 1 living neighbor, then what should happen to this guy? He should die by the next cycle. So that's what would happen to him. We don't know what's going to happen to him because we haven't shown his neighbors at this point, but each one of these cells will get treated identically. This guy looks at the 8 things surrounding him and decides how many are alive, how many are dead, so on and so forth. Similarly, any live cell with 2 or 3 live neighbors lives on to the next generation. So if this guy had 2 live neighbors or he had 3 live neighbors, this guy would remain alive for the next, the next generation, the next iteration of our screen. Something along those lines. Okay. Any live cell with more than 3 live neighbors dies as if by overpopulation. So if we give this guy an extra live neighbor, now he has 4 living neighbors. So the next iteration through, he's going to actually die. Any dead cell with exactly 3 live neighbors becomes living as if by reproduction. So he's currently dead. He currently has 4 living neighbors. He needs to have 3 living neighbors in order to come back alive. So he would stay dead here. But if we got rid of one of his living neighbors, this guy right here now has exactly 3 living neighbors. Any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. All right, so he has 3 living neighbors. So we decide on the next time through, he becomes alive.
Wouldn't that top corner come to life though too, because that had 3 living?
Yeah,
no, it did have 3 living, but it does now.
Yeah, I'm just focusing on this one cell here, pretending like he's our entire world. But yeah, this top corner potentially, I mean, I would want to fill this in with more grid so we can see the guys around him, because he has to have exactly 3 living neighbors, where he actually has a neighbor here, a neighbor here, a neighbor here, a neighbor here. So I'm treating it by a per cell basis. We don't have enough information to choose this cell unless we're looking at it like this is our entire grid. If this is the entire grid, you're right. This guy only actually has 3 neighbors. He has this guy, and this guy, and he has exactly 2 living cells, which I think means he stays alive. So if we're going through this entire thing, any live cell with 2 or 3 live neighbors lives in the next generation, so he's still alive. Then we have this guy. This guy has 1, 2, 3 living neighbors. He stays alive. This guy has 3 living neighbors, and if he has exactly 3 live neighbors and he's currently dead, he becomes alive. So he'll become alive. This guy here has 3 living neighbors, so he'll come alive. This guy here has a bunch of living neighbors. So he has 1, 2, 3, 4, 5 living neighbors. And you can decide if you just want to do this one grid at a time and see the update, that's fine. But really the idea is it's for the next generation. So if I back up here and we go back to what we had, let's just go that route. What you would actually do is you would actually duplicate this like this, and we're going to say, well, I'm going to make my change on the next grid. All right, so the next grid kind of shows up blank, and we decide what's going to happen on this grid based on the current state of this one. So this guy right here is currently dead and he has 2 living neighbors. What happens to a cell that is currently dead that has 2 living neighbors? Nothing. He remains dead. So this guy will remain dead. This guy has 2 living neighbors and he's currently alive. What happens to him? Any live cell with 2 or 3 living neighbors remains alive for the next generation. So he'll be alive. This guy here has 3 living neighbors. What happens to a dead cell when you have 3 living neighbors? Any dead cell with exactly 3 live neighbors becomes a live cell. So he'll become alive. This guy here, he has 2 living neighbors. He's currently dead. What happens? Well, he only can become alive if he has 3 living neighbors, so he stays dead. This guy here has 2 living neighbors. He's currently alive. Any live cell with 2 or 3 live neighbors lives on to the next generation, so he'll stay alive. This guy here has 2 living neighbors, so he'll stay alive. This guy here has 1 living neighbor, stays dead. This guy here has 2 living neighbors, stays dead. This guy here has 2 living neighbors, stays dead. So this is the next iteration of this map. See how that works?
I have another question.
Sure.
Are we always starting with like, are we starting with 1 live cell, or are we starting with no live cells at all, and then we randomly generate cells somewhere or something like that? Or is there like a loop that, like the first loop that passes through to check?
Yeah, we'll randomly,
we'll
give it an initial state. We'll randomly give it an initial state of, you know, 0s and 1s, 0 being dead, 1s being alive, something like that. All right, so this guy right here is a list. Well, this is a list, and it's a list of lists. That's how we're going to represent something that has multiple rows and columns. So we're going to start off by writing some code that will generate our map for us and show it on the screen. So let's do that together. All right, so let's just assume, well, we'll kind of see how big our map ends up getting. All right, so I'm going to go ahead and create a class named, let's call this guy grid. Okay, we'll call class grid, and we'll define underscore underscore init. Underscore underscore. Let me just see something here real quick. And we're going to take in a rows and columns so that we can kind of set up a grid of that size, and we'll initially randomize it. So if I'm going to have, again, we look back here, this is column 0, column 1, column 2, and each column is going to be a list of a bunch of rows. All right, so I'm going to basically have something that has some number of columns. Now I could also think of it as rows. I'm going to have some number of rows where each row holds a column or holds a list, something like this. Okay, we do have something called 2-dimensional arrays, but we're going to represent these guys as lists of lists, which will make sense based on what we already know. So let's go off rows. So we're going to have, in this case, I have 3 rows, and each row has 3 columns. So I need to put a list inside of each of my rows, and I'm going to initially fill it up with, let's just say, a bunch of zeros, just to get something showing up. here. All right, so I need to go ahead and create my grid. So I'm going to say, we're going to do this for rows number of times. So I'm going to say self dot the grid is going to start off as the empty list. And then what I want to do is I want to create an empty list inside of this grid. How many empty lists? Rows number of empty lists. For I in range 0 to rows, self dot the grid at bucket I is equal to the empty list. All right, so that will give me the number of rows there. Now I need the number of columns in there. So I'm going to say for J in range 0 to calls, self dot the grid at bucket I dot append, and I'll just put a 0 in there for right now. So this is going to set up an empty list here, an empty list here, an empty list here, and then fill this guy with 0, 0, 0, fill this guy with 0, 0, 0, fill this guy with 0, 0, 0. And then we're going to display it here so we can kind of see what that looks like. So I'll say def display. And what I want this to do, and I'm actually going to set rows and columns here just so I have it in case I want to use it later. So I'm going to say self.rows is equal to rows, self.calls is equal to calls. So I'll just remember those things, but I'm actually going to be filling in my grid with a bunch of zeros. So we may not actually use rows and columns again because we're actually building what we need right here. So for display, we want it to actually show us our filled in grid with a bunch of zeros, something like that. So we'll go ahead and we want to kind of have a very similar loop to what we have here. So I'll steal this guy and we'll say for I in range 0 to self dot the grid, and I want to get the length of that guy. So this is the same thing as saying rows, the number of things that are in the grid. Then I want to say for J in range 0 to the length of self dot the grid at bucket I, which is another list. And then I'm going to go ahead and I'm going to print self dot the grid at bucket I, bucket J. But I need to do that end thing is equal to the empty string. I think that does it, right? Print hello and is equal to empty string. That might not let me do multiple things in a row to test it. I think that'll work. This just replaces what the last character is by the empty string, so it won't press enter at the end of it. That way I get all the things in the current row. So this is rows by columns, so this will print all the stuff in there. And then after I'm done with that, I'll just print the empty string and that'll kick it down a line. So let's go ahead and just test this real quick. So I'm going to say the grid is equal to a grid. I need to pass a grid, the rows and columns. So let's make this guy 10 by 10 initially. And then we'll say the grid dot display. Grid 10 by 10. Oh, there. I can't say this at bucket I. I actually need to say the grid dot append the empty list. So there's my 10 by 10 grid like this. Really, we could probably make it wider and a little shorter. So let's make it, just to get it to show up on the screen, let's say better. Well, we can actually just say this is maybe 30 columns. That'll make it wider like that. And then let's make it like 8. Something like that. All right, so that's our current grid, let's say. Now we want to randomize this so it's not just always a 0. Okay, so instead of appending a 0, we want to give this guy its initial state. So I'm going to import random. And then here we'll say random dot next int. And what I can say, actually, is it next int? Random dot rand int, I think. And say 1, that'll give me a number between 0 and 1. That's that. This must be the wrong function call. So random dot, is it next int?
It's random, but your semicolon after random might be your import line. I don't know if that's screwing you up.
Oh, well, yeah, it could be. Random dot rand
int, yeah.
That.
Usually you pass it 2 arguments, so you put 0 and 1.
Oh, what's the whole range? 0 to 1. Okay. So there's my random starting position is a 0 and a 1. So this kind of shows our current state of things. Okay. Now, reviewing back from what we dealt with threads last time, I'll just bring up, let me hide this again. We're going to go ahead and create a function for our thread because we want this thread to happen, so often. All right, so we're going to create our thread function here. Let me copy across here. Nope. All right, so we're just going to create a thread function. And this thread function is going to, we don't have to have it take in anything if we don't want, because this guy's just going to kind of do its own thing. We don't need him to, well, actually, we can go ahead and give him the dice object. That'll work, or the grid object, rather. So we're going to say def thread function, or let's call it def game of life thread. And we're going to say that this guy is going to take in a grid. And then what he'll do is he'll tell the grid to display itself. Then he's going to go to sleep for, let's just say, a second for right now. Time dot, so I need to import time and then time dot sleep. Oh. And we'll just sleep for 1 second right now. And let me see, can I do this? I think there's a way for me to clear the screen in Python as well. Python clear screen. It's like a system.clear. Import I think it's just import OS. You know what? We're just going to fake it ourselves. So we're going to go ahead and give ourselves a clear screen thing, because I don't think that os.system we're going to do def clear screen, and this guy is going to not take in anything, and then he's just going to say for I in range 0 to
If you import system, it works.
well, let's try it this way, and we'll see what the performance difference is. So basically, to clear the screen means just make my field of view disappear so something else can appear there. So I'm just going to say to 100. So we're going to maximize ourselves to 100 rows, and then I'll just print out the empty string. So now what we can do is we can sleep for that, and then I'll just call clear screen in here, and I'll put this whole thing inside of a loop. Right, and we're going to go ahead and create our thread. So we're going to import threading, and then we're going to say threading.thread, give it its target, and given the arguments. So we'll import threading, I think. Then down here in main, we don't call display here. We'll go ahead and say my thread is equal to threading dot thread target is equal to, and we call this guy game of life thread. Target equals the name of the thing, and then args and we want to pass it the grid for args. We want to pass it a whole object that could work with. And then we want to tell that guy to start. All right, so here's my thread, and he's built around the game of life thread, passing it the grid as an argument. So now we'll say my thread dot start. Oh, is it just args equals? Yeah, args equals. Okay, it has to be a number that can be iterable. That's okay. Because what we'll do is we will make this grid variable we'll build it inside of our thread. So we'll have them take in no arguments. We'll go ahead and build our grid in here and then let him do his thing. So I should be able to pass this guy nothing. So every 1 second we get a new version of the game. Now, one thing, so we see how slow this is printing to the screen right now, right? I mean, it looks interesting enough, but this is not going to give us that view like we had in here, where it's actually doing this, right? We need to see the entire thing onto the screen much more quickly than what we're looking at right here. And the way to accomplish that, or a way to accomplish that, is to change the way we display. Right now we're printing a whole bunch of times. Now, whenever we print, we actually are telling the CPU to take a break. And I talked a little bit about this when we were talking about threads. Anytime we do input and output, the CPU gets kind of bogged down, gets delayed, something called a context switch. So rather than printing often, what I'm going to do is I'm going to build a string and then print that entire string one time. So I'm going to call this guy the display string, and he'll start off as the empty string. And then what we'll do here is we want to add on to our display string. It's going to be equal to the display string concatenated with. Now we know that the grid at ij holds a number. So we need the string version of that number in order to do concatenation. Similarly, whenever we wanted to kick down a line, we'll say display string is equal to display string concatenated with, that's a carriage return, \n. And then, let me stop this, sorry. After we've built our display string, then we can print our display string a single time. Okay, you see how that's operating differently for us now? Since I'm not printing over and over and over again, I'm getting the entire output once to the screen, and it looks a lot better than having that thing where it was printing out each individual character and then, you know, printing out line feeds and all that stuff. All right, now realistically, we can probably also increase our speed here to like a quarter of a second. It actually might even be too fast for us to see the changes. That might end up working. All right. And now what we can do is we can test to see if this guy works real quickly, just from a visual perspective. We're creating our grid 8:30 here. What I'll actually do is I'll recreate it each time through the loop. That way we get a new random set of stuff, and we'll see if we can, you know, detect it visually changing for us. Yeah, I think I'm seeing some reasonable changes. It's possible zeros and ones aren't the best thing. We might want to do like asterisks and underscores, something like that, or maybe asterisks and spaces. So what we can do there is if I want to map between a 0 and a 1, instead of it being a 0 and a 1 for my random number right here, I can go ahead and say num is equal to random. I'll just steal this part. And then I can say if, let's just say, well, we'll say val is equal to, I'll just make it a space by default. And we'll say if val is, I'm sorry, if num is equal to 1, then val will be equal to maybe an asterisk. And then we'll always append a val. So instead of appending on zeros and ones, we'll append on spaces and asterisks. So now we get a little bit different view.
Cool.
All right. Well, you're about to do the cool part. All right. So now that we have that, effectively, what have we done here with my game of life thread? The only reason we're getting changes right now is because every single time through this loop, I'm generating a brand new grid. I'm kind of faking us applying those game of life rules, right? Because ultimately what we want to have is we want to have something that ends up looking like this, where these are asterisks instead of the little black box. Well, right now we're not going to get these kind of patterns because I'm literally re-randomizing the entire grid every single time. What we want to occur is I only want to create this grid one time. So we'll create it at the beginning of our thread. We'll display it, and then we want to go ahead and apply the game of life rules. Okay, we want to apply the game of life rules to this thing. So, which says create a copy of the current grid, so we can look at the copy and update the original. That's kind of what we did over here when I was walking through it. Where's my keynote? So we created a secondary version of this. So this now is my copy. Oh. So that's my current state of the board. I'm going to go through this guy one cell at a time and apply the rules. So how many alive neighbors does this guy have? He has 2. What do I do if he has 2 live neighbors? I think 2 means he stays alive. If he has 2 or 3, only if he has exactly 3 does he come alive. Let's review those rules. So currently he's dead. He needs to have 3 neighbors to come alive. So he will remain dead. And I might just go ahead and 0 all these out just for visual, but it doesn't really matter because we're going to, whatever row and column I'm dealing with here is the same row and column I'm going to update over here. Okay, so he's dead. How many living neighbors does he have? He has 2. He stays dead. He's alive. How many living neighbors does he have? He has 3. The rule says if he has 2 or 3 living neighbors, if he has 2 or 3 live neighbors, he will continue to live. So this guy has 3 live neighbors, so he will continue to live. This guy has 3 live neighbors, so he will continue to live. This guy he's dead. He has 2 live neighbors, so he'll remain dead. This guy has 3 live neighbors, so he will continue to live. This guy has 3 live neighbors, so he'll continue to live. This guy has 1 live neighbor, which will make him stay dead. This guy has 2 live neighbors. He's currently dead. He has 2 live neighbors. He needs 3 to come alive, so he'll remain dead. This guy has 2 live neighbors. He'll also remain dead. So it's kind of interesting in this case. We didn't actually change anything. So you can see if your grid gets too small, you'll get stuck in a pattern. So we can keep applying the rules of the game of life to this over and over and over again, and this is not going to change. But if we had a bigger grid where each box had more variability, so maybe let's say this was my copy, something like that. And I made these guys all go dark. Like that. Now I'll say how many live neighbors. He has 1 live neighbor, stays dead. He has 1 live neighbor. He becomes dead. Why? Because if you have fewer than 2 live neighbors, you die. So he has 2 live neighbors. Actually, he has 2 live neighbors. So he will stay alive. This guy has 2 live neighbors. So he will stay alive. This guy has 2 live neighbors, but he's currently dead, so he'll stay dead. This guy has 3 live neighbors, so he'll actually he has 4 live neighbors, so he'll stay dead. He has 1, 2, 3, 4, so he'll stay dead. This guy here, he has 2 live neighbors. And 2 live neighbors, when you're currently alive, you have 2 or 3, you stay alive. This guy here has 0 live neighbors, so he will die. This guy here has 2 live neighbors, he'll remain dead. This guy here has 1 live neighbor, he'll remain dead. So we see that we had a small change between these iterations. So you need a copy so that you can say, who are these guys' neighbors? How many live neighbors does he have? And then make a decision based on that. But we don't update the copy. We update our original. All right. So you're going to need to build, have the ability to get a copy of the grid or generate a copy of the grid. In fact, I can even give you that piece. Let's write that real quick. So we can ask a grid to give us a copy. Def get copy. Let's call this get copy of the grid. Now, because lists are passed by reference, I'm actually going to have to build a brand new list and go through and duplicate everything that's currently in my grid. So we're going to say the grid copy starts off as the empty list. Then we're going to go through every element of the grid. So for I in range 0 to length of self dot the grid. So that'll go through all my rows. Then we'll say for j in range 0 to length of self dot the grid at bucket I, and we'll say the grid copy, where each time through here we're going to say the grid copy at bucket I is also equal to an empty list, except I did the same mistake as before. So we'll append the empty list. For j in range 0 to the length of the grid at bucket I, we'll say the grid copy dot append self dot the grid at I j. And then we'll return the grid copy. All right. So this is a version of get copy of the, well, this is a version that built a brand new list of lists called the grid copy and returns it. And we can then apply our rules to the grid copy and then update the grid. So update the grid might mean this. I'll give you that piece as well. Here, let's just test the copy here real quick. I'm going to steal this piece. I'm not going to start my thread right now. I'm just going to go ahead and I'm going to create a grid. I have not indented correctly somewhere. Grid copy, append the empty list. That looks good. J in range 0 to length. There we go. And that looks good. Okay. So I'll go ahead and get my grid. I'll say the grid dot display. Well, we know that's going to work, but then we're going to go ahead and say the grid copy is equal to the grid dot get copy of the grid. And then I'll just print out the grid copy. It's not going to look super pretty because it's a bunch of lists, but we should see that it is a secondary thing. This shows you the whole kit caboodle. If I print out the grid copy at row 1, column 4, that should give me an actual, oh, it didn't. That means I made my copy wrong. Oh, it's the grid copy at bucket I dot append the grid at IJ. So that must have been a space that I tried to print out. Let's so this is row 0, 1, 2. Let's do 2, 0. Should be a asterisk. All right, so this gets me a copy of my grid that I can then apply the rules to. And then I'm going to give you another little tool inside of our grid. So def update self row call new value. And this guy will set self dot the grid at row call equal to new value. Now I can tell a grid to update itself. So right now I'm getting an asterisk there. So I'll go ahead and say the grid dot update to 0. Here, we'll actually force the issue. I'll just put a question mark there. So we'll definitely see it change. And then I'll update the grid copy and print it out again, and we get the question mark. So here I build my grid, has random stuff in it. I display it. Then I get a copy from that. Well, this is a brand new list. And then I go ahead and I print out what I got from the copy, which that guy was actually a space, the thing I printed out. Then I update my original grid to a question mark. And actually, let me, well, and then right now, as I go ahead and I overwrite the grid copy by asking the grid for a new copy of itself. And then I print out what was in that new copy, and notice I had put a question mark where a space used to be. But what I can do here to prove that it is updated by reference is I won't give myself a new copy. So even though I had a question mark there in my grid, it will not impact the copy I have here. So that's a space. This time it was an asterisk. But what's important is it's not a question mark, which tells me I updated my original grid, but it did not update this grid copy that I got before I updated it. So this guy is a true copy of it, a physically separate list of things as opposed to the original. If I want to get a new copy, then I can get that question mark. Okay, so we have these pieces now for building these rules, right? All right, so what we are to do now is go through, and this is going to be inside of our thread. So we're going to apply the game of life rules, create a copy of the current grid so we can look at the copy, look at each element of that copy, and update the original grid using the update method. Then we go to sleep for half a second, clear the screen, display the updated grid. So by applying the rules to this, we should now see those changes. All right, well, what do I need to be able to do when we look at each of these individual things? What do I need to be able to do? If I'm at bucket 0, 0, I need to say, how many neighbors do I have that are, in this case, that are living? How many neighbors do I have that are living? All right. So we might build into, we might build a function that takes in this grid and tells me the number of living neighbors. So let's go here. And we're going to say, I mean, right now, the way I'm getting my copy is I'm getting it as a, well, let's just keep going down this path. This is fine. I don't want to complicate things. So we're going to go ahead and we're going to write another function, def, get number of living neighbors. And this guy is going to take in a grid copy as a parameter, as well as a row and a column. And he should return the number of neighbors that row and col have. Well, that, let's call it a grid copy at position row col have. That's what this tool will ultimately do. Return the number of neighbors that a grid copy row and column actually has. Living neighbors. We come back here. This guy only has 3 neighbors to even look at. This guy has 5 neighbors to look at. This guy has 3. This guy has 3, 4, 5. This guy has 8. This guy has 5, so on and so forth. So you need to account for all possible neighbors given the current row and column. All right, so take a few minutes, try to write this piece. What I'll do is I'll go ahead and post on Slack here the current version of the code. And then what you're going to write is this function called get number of living neighbors. So this guy should return the number of neighbors. That is the number of neighbors that are equal to a asterisk. All right, makes sense what I'm asking you to do? So take a couple minutes, work on that. While you're doing that, I'm going to grab a drink. Okay, so let's take a look at the possibilities here. Forget number of living neighbors. We know the position of those, what those neighbors might be. So we're going to create a count. We'll start off at 0. We have 0 living neighbors right now. All right. Now we know we can have up to 8 living neighbors. Okay, up to 8 different living neighbors. But some neighbors are not legal. Okay, so we might ask, so if we go this route, if I'm this guy, well, if I'm any of these guys, who is my upper left living neighbor? That is row -1, column -1. We need to know if though either of those values are negative. If if I'm here and row -1 is here, then I know I don't have anything up here. If column -1 over here is also negative, I don't have anything there. Okay, so I need to only check if it's a real thing. Okay, now we're going to have a little cheat here to pull this off. And I think I've maybe shown you this in another example, but there's a thing called try catch. So handling exceptions in Python, I can try to do something and then possibly catch the exception. Okay, so let me show you what this ends up looking like. So get number of living neighbors, I can try to do something. So I'm going to try to get the neighbor, the upper left-hand corner neighbor. Okay, so I'm going to try to get a grid copy at bucket row -1, col -1. I'm going to ask a question about that. So if that guy is equal to an asterisk, then count is equal to count +1. Right? So that's what we're going to try to do. Now, this is going to give us an error if row -1 and col -1 are illegal positions. Now, we could have asked, we could have said, well, if row -1 is negative or col -1 is negative, if either one of those two things are true, then we are, then we're not even going to check. We're not going to even try to see if it's equal to it. But in this case, I'm using try catches to say, look, I'm just going to try to do something that might be illegal. And you're going to let me try to do it, but I might run into an issue. And if I run into an issue, I'm not going to do anything. So maybe we just have a count of illegal neighbors just to keep track of that for no good reason, just so we have it, is equal to that +1. All right, so we're going to try to update count based on my upper left-hand corner neighbor. Now we'll do some more tries. We will try to look at the neighbor right above us. Then we will try let's look at the neighbor above us to the right. Then we will try so then we'll try to look at our current row, but the guy directly to our left. Then we'll try our current row, the guy directly to our right. Then we'll try the next row, the guy to our lower left. We'll try the next row, the guy immediately below us. We'll try the next row, the guy below us to the right. And then we'll return the count. How many things we found in there that were, well, how many neighbors were alive. All right, so this function, let me make sure that I don't have error messages in here. Isn't it called accept?
It's just indented.
Oh, I have mine indented. Oh,
Yeah.
Thank you. Let's do that. This thing scrolls so fast. Yeah, the accept is part of the try. All right, it's fine with it now. And then we'll go ahead and test this guy. So get number of living neighbors. Set the grid copy, and let's pass it row 0, column 0, that upper left-hand corner. So we got 4 living neighbors there. Let's kind of look at that. So here's that upper left-hand corner. Is that it? 0, 0. I'm going to get rid of this. This should not be 4.
I was told during that video game thing that we were making that the numbers, as you go down a row, it's actually opposite, like negative.
No, I mean, because it's up to us how we want to
Okay.
handle rows and columns. So as long as we're consistent, it should be fine. But yeah, our count is off here. But in any case, once we have this working, so we'll review this at the beginning of class next time. Once we have this guy working, we should be able to then pretty easily apply our 4 rules and call update on our grid and get this guy to run, giving us our game of life. And then we can change the size of our board and all that jazz. Okay. And then using threads, it allows us to kind of give it that pulse where it does it, then does it, then does it. Well, actually, we could do that just with a timer, but having it run in its own thread would then allow us to potentially have multiple threads of it running at once, and then even display all of them on the screen at the same time. So we kind of have multiple games all running simultaneously, and that could be kind of interesting. Okay, so no homework over break. So the next time I'll see you is on Tuesday. Remember, next week is the last week of classes before final exams. So on Tuesday or Thursday next week, we'll talk about the final exam. But the final exam I'll put up probably on Sunday night, the Sunday before finals. And you just have to do it sometime before the end of that week. You'll have to do it all in one sitting, but you can decide when you want to do it because it's going to be an online exam. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Tuesday.